So for the computer revolution, as you know, is already like happened that fast and rapid progress. All of these computer technology is followed the Moore's law, as we will see later on. But there are a lot of applications in automobiles and cell phones, even in medical stuff, human genome or World Wide Web search engine and stuff like that. We have a lot of these things. Classes of computers, of course, as everyone is familiar with the desktop or the servers, they are general purposes. Just the server might be a little bit with higher capacity and performance and reliability and so on and so forth. Another class is the embedded computers, which would be like for a certain particular tasks. It's not like as general as the desktop or the server, but a lot of the companies that has a certain particular products doing a certain tasks, they might refer to the system or using like an embedded systems that most probably an experience that whatever you are taking here in this class might be very helpful to them. So things that we will learn, we'll see like how we can transfer a higher level language to a machine language throughout like the assembly. So we'll understand in details the assembly, how it works, how also the data path, how we can define the performance, how we can do some enhancements into our design, and also the pipelining. We'll see like the cache memory and stuff like that. We will not go that deep in the parallel processing, just like concepts, but we will not be heavily covering these kind of things. Of course, under that, we see like some of the algorithms. We'll see how we can transfer the assembly language to a machine language, the whole data path of the processor from just the very first input until I have the output, how everything is processed and executed. Also, we'll see how the interface between the processor and the main memory, and of course, by the same concept with the cache memory. Also, we'll see at the very end an input-output systems. So each of these things will have approximately a particular chapter to cover. So just as a rule of thumb, you have an application software at the very top here. And then this is written in a high-level language, which we refer to as HLL, higher level language. Underneath, you might have the system software. This system software is just like a compiler, which will translate this HLL code to a machine code. So it goes, of course, to assembly and then to a machine code. The operating system will handle all of the input, output, and managing the memory and stuff like that. However, in our case, we will more be concerned just about the hardware design with the processor and the memory and the input-output interface, since we are designing everything by ourselves over the FPGA. So it's not like having like a CPU that we will have an operating system and we will have another design. In our case, we will build everything from scratch. So just for your reference, when you write a language with the, let's say like a C language, it's a high level language programming. It can be Java, it can be Python, it can be C++, it can be C#, it can be whatever. It's just a higher level language, HLL. This is an example for that. After this, we have what we call the compiler. And the compiler is not but transfer this higher level language to assembly language, as you can see here. This is an assembly language, which is a little bit lower level language, which is talked directly to the machine. And of course, if you write your code in a lower level language, most probably you can control more and you can enhance the performance in a much better way, and so on and so forth in most of the cases, if you are a professional in writing that particular assembly code. After that, you have an assembler that will translate your assembly code to what we call the machine code. And as you can see from here, the machine code is not but zeros and ones. And this is what the machine understands, zeros and ones. What we understand, we can write. I mean, we can write a language. We can write a language, as you can see from here. But for the machine, it will not understand this. It will just understand zeros and ones. What we will learn, that actually we will manually understand or learn how to go from this to this, and also the vice versa, how to go from that to the other assembly language. We'll see that. Just like as one thing that I would like to highlight, if you count the number of lines in this instructions of the assembly, 1, 2, 3, 4, 5, 6, 7, if you count the number of the machine language zeros and ones, 1, 2, 3, 4, 5, 6, 7. So they are the same. It just gives us an indication that each of these lines be transferred to one of the lines of the machine codes of the zeros and ones. So each of the instructions has been transferred to one line of zeros and ones. We will understand in detail how we can do that. So as soon as I will see this, how we can get that. Or as soon as I will see this, how we can get that, and so on and so forth. So this will be covered in details. So just like, again, as a review, the components of a computer, assuming that you have a desktop server or embedded computer, then you have a user interface device, you have storage device, and then you have a network adapter. Our concentration will be actually on the CPU itself and the main memory. This will be our concentration. We will not concentrate, at the very end, the input output, but we will not concentrate on the network adapter and stuff like that. So if you see like the computer, you have a lot of stuff. What we are concentrating on is just the CPU that we have, and also the memory that we are interfacing with. So inside the processor, we have a data path which performs operation on the data, and then we have the control, or we can think of this as a brain, which will control, of course, how we would interface or how we will move forward with the data path and the memory and stuff like that. And then there is a memory. We'll see like there is different type of memory. There is main memory, there is cache memory. We'll see like the cache memory is small but fast, depending on this technology, the SRAM or static RAM. We'll see also later on what are the difference between SRAM and the DRAM, what are the pros and cons of each of them. So inside an AMD, we have 4 processors, for example, cores. This is 1, 2, 3, 4. Inside one of these core, as you can see, we have load and store, we have execution, we have fetch, we have some also cache and stuff like that. We will design all of these things by ourselves. We will design it. Each of these things will be covered in a certain approximate chapter, and then we'll see how we will go over this kind of stuff in terms of the design, and you will end up by the end of the semester design a CPU or mini CPU over an FPGA. In terms of data storage, just for your reference, there is a volatile main memory, and also there is non-volatile memory. The volatile memory, like as an example, the RAM, which as soon as you remove the power, it just like remove all of the data. However, with the disk or a flash memory or optical, whatever, it's non-volatile since when you remove the power, it's still there. But just to highlight that we will not, go that further in this kind of stuff. We are just concentrating on the main memory and cache memory, and not in terms of power, but in terms of data handling and why it is there and stuff like that. There's another thing also, which is not concerned about this course, which is the network. We have LAN, WAN, Wi-Fi, Bluetooth, but this is covered in another course. As you can see, in terms of the technology enhancements, we begin in 1951 with the vacuum tube, but we end up in 2005 with the ultra large scale, and can you see like millions of components, and even now going more and more and more. So just like the technology is going fast and fast and fast. Some expressions I would like you to be familiar with, for instance, the response time. And the response time is just how long it takes to do a certain particular task. So if I'm giving you a task, certain task, and then you return to me with your feedback after a certain particular time. So this is your response time. If you take 1 minute, so your response time is 1 minute. If you take 1 second, your response time is 1 second. It's the same exactly things with the CPU. I might give a task to a CPU and then just calculate the response time. Of course, when you have less response time, so this means that you are faster. So this means that gives you an indication that you have a better system in this case. Also, the throughput, which is the total work done per unit time. So you can finish all of this work per unit hour or per unit minute or per second or whatever the thing is. This is the throughput. Of course, the more work that you can do per unit certain time, this means that you have a better performance. But if we were to ask how are responses time and throughput affected by first replacing the processor with a faster version? Meaning, if I have now a better processor, what is or how this is affecting the response time or how this is affecting the throughput? A rule of thumb, of course, in most of the cases, if not all, if I have a better processor, I will get less response time, which again, better performance, and the higher throughput, which again, better performance. But does this exactly the same in the case of adding more processors? So if I will add more processors, will always my response time will be less? Or will always my throughput will be higher? Unfortunately, this is not always the case, because you might have a task that just one CPU, one normal CPU will be able to finish it. If you add more than that, it might even get worse, because adding of all of the data handling and parallel stuff and organization and data distribution, it might add overheads that will increase the response time and it will reduce the throughput. So it's not always the case. And that's why we have to be very careful on assuming that I have decided to do parallel processing. First, will parallel processing will help or not? Second, with how many processors to add? So I might add 2 and this is sufficient, but I might add 4 and this will be sufficient. And anything more than that will not be helpful at all. It might actually go in the opposite direction. So all of these kind of things we need to be aware of. Nevertheless, we will not concentrate on the parallel processing in this particular class. We'll concentrate more in the response time. That's why we'll introduce the pipelining and how we can get a better response time at the very end using this kind of a technique. Suppose that we need to calculate the performance with this easy concept, meaning we will define the performance as just 1 over the execution time. As simple as that. So if you have system X that is n time faster than system Y, so basically the performance of X divides the performance of Y will be equal to the execution time of Y divided by the execution time of X, since they are reciprocal to each other. So let's take that example. Suppose that time taken to run a program on A is 10 seconds, on B 15 seconds. So execution time of B divided by the execution time of A, when you do this division, give you 1.5. This gives us an indication that A is actually 1.5 times faster than B. So with this just easy relationship, you can get a sense of which system is better than the other. Of course, we'll go much more deeper with a little bit more complicated formulas and stuff like that, but this is just to give you an indication of the performance. Another also expression that I would like you to be familiar with is the elapsed time. We mentioned the response time. Here, the elapsed time, which is total response time, including all aspects like processing, input, output, overheads, idle time, and stuff like that. Everything. This is the elapsed time. It's everything. But the CPU time is just the time spent processing a given job. Will not have all of these kind of things of overhead, of idle time, and stuff like that. It's just the CPU time. We will remove any input outputs time or any other jobs for sharing and stuff like that. And generally, different programs, of course, will be affected differently by the CPU and the system performance. So let's go a little bit much more deeper in how we can get such differences in the performance. So Suppose that you have a certain particular system, and this system is working with a certain particular clock cycles. With these clock cycles, we have in this situation, as an example, 1, 2, 3 clock cycles. So the first clock cycle is here, 1. Second is here. Third is here. And this one of these is called the clock period. We will refer to that as T, for example. And if I would like to ask, for instance, what would be the period, the total period or total response time or total CPU time, let's say. We need to calculate the total CPU time for a certain particular task. What information do you need to know in order to calculate what is the CPU time? First, of course, you need to know what is the clock period time, what is T. But not only that, you need also to understand or to know how many T's did you need or did you already consume to finish the task. Correct? And when you multiply this by this, then you can get the whole CPU time. I may say, like as an example, in this particular case, assuming that your task finish here. So you have 1, 2, 3. So you have 3 multiplied by T. This is actually the CPU time in this case equals 3T. As 3 is the instruction count or the number, or let's say, no, sorry, the number of cycles, not the instruction count, the number of cycles multiplied by the period of one cycle. Correct? So the whole CPU time will be equal to that. So suppose that this T is 0.25 nanoseconds. So it's actually 3 multiplied by 0.25 nanoseconds. One other thing I would like to highlight that we can also calculate the clock frequency or the rate from the T. How? F is equal to 1 over T as an example. So if it is equal to 1 over that, so the frequency will be actually 4 gigahertz or 4,000 megahertz in this case. So again, just like to review whatever we have mentioned, that the CPU time is not but how many clock cycles. In our previous examples, we have 3 multiplied by the clock cycle time, which was in the previous slide as T. Then you know the CPU time, correct? And we also mentioned that this T is not but 1 over F. And because of that, I will remove this and I will just write 1 over F, which is the clock rate, because the frequency is just the clock rate. So at the very end, the CPU time is equal to the clock cycles, number of clock cycles, which is 3, divided by the frequency. And from that, I can calculate the CPU time. How I can improve the performance of the CPU time? Improving the performance of the CPU time, meaning I would like this to be less. How this will be less? By this going less, correct? Because if I have less number of clock cycles, this CPU time will be less, so I have a better performance, correct? Another option to do what? To increase the clock rate. When I'm increasing the frequency, then again, if I increase that, this will be less. So this is also another option of improving the performance in this particular case. But now I give you as an input that we have CPU clock cycles. We have 3 clock cycles, and each one is T. So T will be given because this is just a processor or whatever FPGA that's work a certain particular frequency and stuff like that, or you might use to define it. But how you will know that you need actually 3 clock cycles in that particular task? We need to go a little bit much deeper to understand. But before that, let's take that example. Suppose that we have computer A that is 2 gigahertz clock and 10-second CPU time. We are designing computer B that is aimed for 6-second CPU time and can do faster clock but causes 1.2 clock cycle. How fast must computer B have in as a clock, as an example? Just apply the same equation that we have. The clock rate is equal to the clock cycle divided by the CPU time. What we had earlier, CPU time is equal to the clock cycle divided by that, but it is exactly the same thing. You can put this here and this here. I mean, this is just like an easy set things to do. Okay, so this is for B. Clock cycle for B is what? Is given 1.2 multiplied by the clock cycle of A. 1.2 multiplied by the clock cycle of A. What is the CPU time for B? The CPU time for B is basically 6 seconds as given here. So it is 6 seconds. So our task is to calculate these clock cycles for A. How we can calculate the clock cycles for A? Clock cycles is CPU rate multiplied by the CPU time. So this multiplied by that, it will give you these things. This is what we have: CPU clock cycle, CPU time multiplied by the rate. What is the CPU time for A? Is 10. So it is 10. What is the clock rate for A? It is 2 gigahertz, 2 gigahertz. So multiply this by this, I have that number. Plug that number here, then you have the clock rate for B is equal to 4 gigahertz in this particular case. So you can see like the B, of course, has now a clock rate of 4 gigahertz instead of having A as a 2 gigahertz, that example. So as I mentioned, we need to go a little bit much deeper to how I can calculate the clock cycles. We have already indicated that the CPU time is equal the clock cycles multiplied by the clock cycle time. It was 3 multiplied by T. So assume that there is nothing here. This is just 3 multiplied by T. But how I will know that this is 3, or how I will know that this is 4, or how I will know that this is 5, or whatever the number is? How I can know that? First, do you remember the example that I mentioned at the very beginning when we have an assembly code which we count as 7? Correct? And each of these instructions will need a certain particular clock cycle. Correct? Suppose, just as a given example, that each of these lines will need 2 clock cycles. And I'm asking you, what is the total number of clock cycles? So 2 multiplied by 7 will be equal to 14, because 2 per line, we have 7 of these, and the 2 multiplied by 7 will be equal to 14. So instead of 3 multiplied by T, in that example, it will be 14 multiplied by T. So now I know how I can calculate the clock cycle. The clock cycle is not but the instruction count. How many instructions do I have? Multiplied by the cycles per instruction that we refer from now on as CPI. So you need to be familiar with that. CPI, cycles per instruction. Plug this here. So the clock cycles is equal to the instruction count multiplied by the CPI. And this is CPU time already multiplied. We have it that this guy multiplied by the clock cycle time. If you do these things, so this guy is again here. The clock cycle time is 1 over the F, and that's why it is equal to 1 over clock rate. So here with this example, we have seen that we know, or we understood how we can calculate the clock cycles. We can even go much more deeper than, okay, so how did you know that each of these instructions will be equal to 2 as an example? Or the other way around, does this mean that all the instructions will have a 2 CPI, 2 cycles per instructions? Maybe you have an instruction that is difficult, correct? Maybe you have an instruction that is easy to execute. So it doesn't have to be always 2. What will be the clock cycles in that time? This is what we will see. Also, can we calculate an average? Also, these things we will be able to see it. But before that, let's take that example. So computer A, cycle time is given, CPI is given. Computer B, cycle time is given, CPI is given. And both of them has same ISA. ISA is, and you need to be familiar with this, is instruction set architecture. Same ISA. Which one is faster and by how much? Okay, we'll just apply the formula that we had from the previous slides. CPU time is equal instruction count multiplied by the CPI multiplied by the cycle time. Instruction count multiplied by CPI multiplied by the clock cycle time. This is what we have. And since we have A, so this would be for A and this would be for A. How much in instruction count? I don't know. The only information that I know that both of A and B, they have the same instruction set architecture. So both of them have the same number. And we refer to that as I. That's why we have this as I. CPI for A is 2. So it is given just the 2. Time is 250. So we have 250. If you do this multiplication, it will give you that number. Let's apply the same things for CPU time B. Instruction count, CPI B multiplied by this. Instruction count, we don't know, but we know that it is I since they have both the same instruction set architecture. CPI for B is what? CPI for B is 1.2. How about the cycle time? 500. All of this, it gives you this. Then you can just divide this by that. It will give you that actually CPU time of B is 1.2 multiplied by the CPU time of A. So which one is better? CPU time of A, of course, is better because actually the CPU time of B is taking more time than the CPU time of A by 1.2. So in this case, CPU time of A is less. So the CPU A is or has a better performance in this particular case. So as I mentioned, if suppose that going back to the same example that we mentioned, that we have 7 lines, 1, 2, 3, 4, 5, 6, 7. And I gave you an example that each of these lines will take 2 CPIs. Suppose that this is not the case. Suppose that this one has 2, this one has 3, this one has 4, this one has 2, this one has 3, this one has 5, this one has 3, for instance. How you calculate the total clock cycle, total number of clock cycles? You just add all of them, correct? 2 plus 3 plus 4 plus 2 plus 3 plus 5 plus 3. But since we know what is multiplication is, so instead of doing that, we can say 2 multiplied by how many times? It's 1, 2. So 2 multiplied by 2 plus 3, how many times? 3, 1, 2, 3. So 3 multiplied by 3. Plus 4, how many times? 4 multiplied by 1. Plus 5 multiplied by 1. Whatever the number is, you know now what is the total number of clock cycles. And this is exactly what we have in this formula. The summation of the CPI multiplied by the instruction count. So the instruction count in this case, the instruction count in this case was the CPI was 2, and then the instruction count was 2 in this particular case, and then plus this, plus that, and so on and so forth. So it gives you the total number of clock cycles, correct? Suppose that I need to get a sense of how much is my average CPI, cycles per instructions. So here I have, for instance, 2 cycles in this instruction. This is 3, this is 4, this is 2, this is 3, this is 5, this is 3. I'm telling you, please give me the average. How you can calculate the average? Exactly the same way that you will think if you would like to calculate the average of the students. And instead of 7 lines, calculate 7 students. And this is the grade of each student. How you calculate the average? Add all of them, divide by the number of students. If you add all of them, divide by the number of students, this will give you the average grade of the class, correct? Here, exactly the same things. I know the cycles, cycles needed for instruction 1, the cycles needed for instruction 2, and so on and so forth. I will add all of these, divide by the total number of instructions or the total number of students. Then it will give me the average grade or the average cycles per instructions. Roughly, with this code, how much is the number of cycles per instructions? I can calculate it that way. And this is what we have here. This clock cycle that we mentioned, divide by the total number of students or the total number of my instructions. How we calculate this is just by this, and that's why we have this guy here, and then we will divide by the number of instructions in this case. Please note that this has I, this has I, this has I, because it differs between line and line. But in this case, the instruction count is just the total number. It just does not have I. This is just like the total number known in this particular case. So let's take that example. So now we have classes A and B and C, A and B and C. And they're giving me the CPI for each of these classes. So the cycles per instruction for class A is 1, B is 2, C is 3. And they're also giving me an instruction count in sequence, one of the sequence, and the instruction count of another sequence. And we would like actually to calculate the same things. I would like to calculate basically the CPI on average. How I calculate the CPI on average? First, calculate the clock cycles and then divide it by the total number of instructions. How to calculate the clock cycles? It's CPI multiplied by instruction count plus the other CPI multiplied by its instruction count, and so on and so forth. This is what we will do here. So for instance, calculate that for sequence 1, we'll multiply CPI by the instruction count plus this by that plus this by that. If you do this, it will give you 10. Divide by the number of counts, number of instructions. What is the number of instructions? 2 plus 1 plus 2. So the total number of instructions is 5 in this case. So 10 divided by 5, the average CPI is equal to 2. Let's trying to do the same things with the sequence 2. Again, CPI multiplied by the instruction count, CPI multiplied by the instruction count, plus the other one multiplied by the instruction count, plus the other one multiplied by the instruction count. All of this is here. 4 multiplied by 1 plus 1 multiplied by 2 plus 1 multiplied by 3 will give me 9. I need to calculate the average CPI. So it's 9 divided by the total number of students or the total number of instructions. 4 plus 1 plus 1 is equal to 6. 9 divided by 6 is 1.5. So this sequence, the average of CPI is 2. This sequence, the average of cycles per instruction is 1.5. So which one has a better performance? Of course, the one with the less number of cycles per instruction. Or if I'm giving you like this class has an average grade of 2, this class has an average grade of 1.5, and which one is better? Of course, it will be the other way around in this case, because higher grade will be better. But in our case, here with the cycles per instructions, I need less number. So the less number would be better, but on average. So I can judge right now on average what will be these cycles per instruction for that particular sequence. So just as a summary with this CPU time, we mentioned that at the very end, CPU time is what? Seconds, correct? Or seconds per a certain particular program. And we calculate that by multiplying, as we have seen here, the instruction count multiplied by the CPI multiplied by the cycle time. So we can have it here also instruction per program multiplied by clock cycles per instruction multiplied by seconds per clock cycles. In order to make sure that this is conceptually correct, this will go with this will go with this in terms of units. This will do of this, and at the very end is just how many seconds per certain program, which is the CPU time in this particular case. So now let's move to the structure that we have in the computer. So the computer here as a total will have a couple of stuffs: input, outputs, main memory, and the CPU, and also something that to connect all of these things, I will refer to that as system bus. If we look closer to the CPU, inside the CPU, I have multiple components. We have an ALU, which is arithmetic logic unit. We have a registers. We have a control unit, which is the brain of the CPU. And also we have an interconnection bus. If we look closely to the control unit, we have a lot of sequence logic, control unit, control memory, and so on and so forth. Just again, we will design the whole things by ourselves. All of these things, you will design the registers, the control, the ALU, all of these kind of things. So no worry about that. You will design it in details. CPU is just control, of course, the operation of the computer. We have a main memory as a storage place. We have input outputs that will just move the data between the computer and the external interfaces or environment. And there is, of course, an interconnection that will connect all of these things together. Our control unit or the brain is just control the operations of the CPU. We have the arithmetic logic unit will do all of the arithmetic operations. The registers is not but a storage which is internal inside the CPU. So you can think of this as a memory, but it's a very small memory which is inside the CPU. We refer to that as a register. Of course, I mean, we hope that we have a big storage as a main place storage unit inside my CPU, but practically this is not possible, unfortunately. And then we will have the interconnections. Also, we have another type of memories called the cache memory. We'll also cover this in a whole chapter later on, a lot of details. But just for now, you might need to think that we might actually have or needs to include multiple layers of memory between the processor and the main memory, and that's why we will add the cache. It's like much faster than the normal memory. Nevertheless, it has less storage. You can think of this related as an apartment, for instance, and inside this apartment, you have a storage unit, but of course it will be a small storage unit. So this apartment will be like as your CPU, but the storage inside this apartment or inside the CPU is small and limited. You hope, of course, that you will have a great storage unit, but in an apartment, this is not possible or not practical. In order to get that, you have to go to another storage place that actually have a better and larger place, for example. Here is exactly the same. In order to have something in between, you might need to have a little bit of a space between you and the whole storage unit. And then you might create another space in the building or stuff like that, that the company can create as a middle place between you and the main storage unit. And that's why we have these concepts, what we call the cache. We'll explain in details the cache memory. As we mentioned, again, the processor have all of these kind of things. Inside the core, we have all of these systems which you will design by yourself. So no worries about that. So Moore's law, as we mentioned earlier, what Moore mentioned in 1965, that the number of transistors that could be put on a single chip was doubled every year. And I mean, the nice thing that approximately we followed that rule. By the way, Moore, or Gordon Moore, he was a co-founder of Intel. Interestingly, we find that has approximately a trend like that as expected, goes approximately double each year. But again, at the very end, we have to reach like a certain particular threshold. And because of that, another kind of computings came into place, like quantum computing and stuff like that, just like to increase again the performance without or with the limited amount of number of available components and stuff like that. One of the other limitations that we have in our design is the power. So we would like to enhance the efficiency, so increasing maybe the frequency, but again, the power will be increased. There is limitations. We can reduce the voltage, but also there is limitation. We cannot go beyond a certain particular number. Here is how we calculate the power is equal to the capacitive load multiplied by voltage square multiplied by the frequency. So the voltage has been reduced from 5 to 1 or even to less than 1. Frequency has been increased, so the power, of course, will be increased. So this means that if we have more logic and the clock speed, then we'll have a higher power. So this means that we will have more heat, and more power That's of course a big problem, because this will dissipate heat and it might burn the CPU, or it might also at the very end you might need to add like fans and stuff like that to cool down, or another technology. So again, more money and more overheads. It will also add what we called RC delays. So these RC delays will be added, and all the interconnections will create actually this kind of delays, which with high speed CPUs or with high speed systems will actually create problems. Even with microseconds will create problems. So we need to be aware of all of these kind of things. Also, another problem, the memory latency. The problem that the CPU is a lot faster than the main memory. And because of that, you might actually ask for something from the main memory and you just wait idle, or whatever we will explain later on how we can enhance the performance. But at the very end, this limits the performance of the CPU by just waiting for nothing, just waiting because the memory interface is slower, a lot slower than the CPU. And that's why one of the examples, or one of the reasons we had to use the cache memory. Nevertheless, still it's not as fast as the CPU or as the register, for example. Let's take that example to see like the reduction of power and what is the limitations. Suppose that we have a new CPU which has 85% of capacitive load than the old CPU. We have also 15% voltage and 15% frequency reduction. First, I will calculate the P old, C multiplied by V square multiplied by F, exactly like here. C multiplied by V square multiplied by F. And then the P new, it says here 85% of capacitive load, so it is 0.85 multiplied by C old. 15% voltage reduction, so again it is 0.85 multiplied by the V old, and then a square. And then 15% also frequency reduction, so F old multiplied by 0.85. If you do the math, you will end up with 0.52. So P new is approximately half of the P old. So at the very end, I have been able to reduce it to half. Nevertheless, we can't reduce the voltage further, so there is still amount of bottleneck or threshold that I can't actually go beyond. So we can't remove more heat. So how we can improve the performance in this case? One of the options to do is the multiprocessor. So we can have multi-core microprocessor, then it might enhance the performance. But also, on the other hand, it will add a lot of other complexity. How I can do the load balancing, how I can program for a certain particular performance. All of these kind of things is difficult. How I can optimize the communication and synchronization. So again, there is trade-off. You will get something, but there is also another thing that you might lose, or you add an overhead and stuff like that. But nevertheless, definitely multiprocessor in most of the cases have been able to increase the performance and the throughput. And you can see from this, of course, the GPUs and stuff like that, which has increased a lot the performance. But again, a lot of heating, a lot of dissipation and stuff like that. So this is just for your information that at the very end with the CPU, the manufacturing the ICs, and then this is from the very beginning, and then they slice it, and we have like a certain patterns, and then they test the dies, they remove like the bad dies, package it and stuff like that. At the very end, you have something like that. This will be the wafer. One of these matrix will be like a certain particular chip to do a certain particular tasks. For instance, as you can see, this needs actually a huge amount of work, or maybe like also it needs like a high end quality and performance for a certain particular manufacturing and process that would be able to create these kind of things. I'm not sure if you knew this or not, but in old days, several years ago, maybe like 60 or so, we didn't have the computer with this size. It was like very, very large in size, because we didn't have like the technology at that time to build this kind of wafer, millions of transistors, just in a very small chip like what we have right now. But all of these things, I'm not expecting that you will remember, just for your information. Okay. Another important principle that we need also to highlight is called the benchmark. So what is exactly that? Suppose that you have startup companies and it creates like a certain particular products, let's say a CPU. And you would like to compare or to know if this CPU is with high quality as other competitive companies or not. How you will know that? There should be like a certain way to decide if this product or if this CPU is better than the other or not. Or if you have like two companies and you would like to compare between them, which one would be better than the other and stuff like that. So you need to have a benchmark. And actually to create a benchmark, there are other companies that are very specific in this kind of tasks, that they build a benchmark in order to compare products. So you can know that this is better than this in that particular tasks and so on and so forth. So in order to have something like that, it is feasible, but this benchmark has to satisfy or to follow a certain particular characteristics or rules. For instance, it is need to be written in a high level language, which will make it portable across different machines. Why is that? Because I can't write this to assembly for a certain particular processor, which will be optimized for that processor, and it is not optimized for another processor. And this will not be fair. So I wouldn't be able like to write an assembly for a certain particular company, which will not be the same as the other company. So the performance wise, of course, would be biased toward that company that I have built my assembly with. And of course, in order to be fair and portable across all different products or CPUs, then it has to be written in a high level language. Also, it needs to represent a certain particular domain. For instance, as an example, you can create a benchmark to compare numerical programming or this commercial programming or system programming or whatever the thing is, because I can't make a benchmark for everything. It would be difficult. We need to be a little bit more specific that this product is better than this in numerical programming. This would be better in commercial and so on and so forth. Also, it can be easily measured. Of course, this is something I think should be approachable, but one of the rules that we need or characteristics that we need to follow. And at the very end, of course, it has a wide distribution. One of famous benchmarks called Standard Performance Evaluation Corporation spec. This spec CPU 2006, it just used the geometric mean of performance ratios. You can just follow all of these kind of things. At the very end, calculate the square root of all of the geometric mean of the execution time ratio, as you can see from here. So with this spec CPU 2006, this is a well-known benchmark. I just would like to highlight a couple of things, that this consists of 17 floating point programming written in C or C++, 12 integer programs written in C or C++, and have 3 million lines of code. That's why we can agree that actually in order to have something like that, we need another company to create this kind of codes. And this might be only one of the domains and not the others and stuff like that. So it's actually has to be by itself a new company that should be able to do this kind of comparison. So here is Amdahl's law. So what is Amdahl's basically mentioned? He would like, or the basic idea behind Amdahl's law is to see what would be the potential enhancements in my system if I would increase a certain particular task, or if I will use, for instance, a multiprocessor or so. Will this be possible or not? We need to get a sense of that. So this can be generalized, of course, to evaluate and design technical improvement in computer system. So if you have a certain particular things to do, or if you do a certain particular enhancements with these particular CPUs. Will this be possible or not? Let's take a little bit of more details about Amdahl's law. So this improving an aspect of a computer and expecting a proportional improvement in the overall performance. So here the time of improvement is equal to the time affected divided by my improvement factor plus T unaffected. So at the very end, my improvement, the time improvement, will be the time that I didn't touch, is not affected by any enhancements, plus the time after the enhancement. And how I can get the time after the enhancements? It is the original time divided by the improvement factor. So I am adding, as an example, 2 processor to get it like a half, or 3 processor to get it as 1/3, and so on and so forth. So let's see this in a little bit, in much more explanation by an example. Okay, so here it says like a program runs in 100 seconds on a computer. So the total here is 100 seconds. The add operation, it needs 60 seconds. The all other instructions requires 40 seconds. So I have a certain particular program, it has an addition, other tasks, but the addition by itself, it consumes 60 seconds out of the whole 100 seconds. Okay, that's fine. What's next? Suppose that I will decrease this time, the addition time, instead of 60, I would like to decrease it by half. So the improving factor by 2 times. So it will go from 60 till 30, correct? Here, 60 plus 40 was 100. So the total time was 100. Here, it's 40 plus 30. 40 is still the same. I didn't touch it. This is the T unaffected. I didn't touch it. This is still exactly the same. I didn't enhance it. The only thing that I have enhanced is the addition operation. So I went by improving factor of 2. It went from 60 to 30. So at the very end is 70. And this 70 seconds is speed up of 1.4. It's compare 70 to 100. It is 1.4. Okay, that's fine. I can do even further improvement. Instead of 2, I need to improve it by 4. So 60 divided by 4, it will give me 15. The total time in this case, 40 plus 14, will be 55 seconds, which is speed up of 1.8. Can I do better? Let's see. I will improve to the extent, which is not practical, but just to the extent that the addition operation will take 0 seconds. It's nothing. At the very end, I still have the 40, correct? I still have the 40 comparable to 100. It is 2.5 times faster. This is the maximum that I can achieve. I have reduced the addition operation to 0, yet I haven't been able to get more than 2.5 times faster. So there is a threshold. I can't go beyond that. Correct? And this shows you here that thing. Okay, so going back to Amdahl's law, the execution time after improvement, all of this, here is 70, here is 55, here again 55, 40, is the execution time unaffected. Usually the blue 40, 40, 40 is always there, plus the enhancement. The enhancement is not but the execution time before the improvement, which is 60, divided by the amount of improvement. In this case, 60 divided by 2 is 30. So I have added 30 plus 40. In this case, 60 divided by 4, it is 15. 15 plus 40, this is another thing. And then the other last one, that this actually total of these is 0. 0 plus 40 is still 40. Okay. So going back to this slide again, let's see that example. Multiply accounts for 80 seconds out of the whole 100 seconds. So we don't have here an addition operation, we have a multiplication operation, and this multiplication is 80 seconds out of the whole 100 seconds. And the question is, how much improvement in multiply performance to get a 5 times overall performance? In the previous example, we have received 2.5 overall performance. Here, I'm asking you, I'm giving you the target performance, I need to be 5 times faster. How much enhancements I need to do to the multiplication to achieve this target? Is it possible or not first? And if it is possible, how much enhancements I need or improvement I need to do? Let's apply that into Amdahl's law. T improved is how much now? It says 5 times faster, correct? It was 100 seconds, so 5 times faster means 20 seconds, correct? 100 divided by 5, it's just 20 seconds, correct? So 20 will be here. This is the time improved. T affected is the 80, is usually there. Divide by the improvement factor, this is unknown, I need to know. Plus the T unaffected. The T unaffected is what? I'm telling you here that this whole task is 100 seconds. And I'm giving you that out of this 100, you have 80 seconds for multiplication. Correct? What is the T unaffected? Is these things. Do you remember the 40 in that example? Here it is 20. Correct? So this is 20. So 20 unaffected. So back to this equation, 20 is equal to 80 divided by n plus 20. What is the n? In this case, n is infinity. Correct? So I can get a 0 term. But is n infinity will be possible? Practical case? This is impossible. So I won't be able to get a 5 times faster, no matter I will do in enhancements in the multiplication basically operation in this particular case. Okay, so we can take also MIPS as a performance metrics. What is this MIPS? It's millions of instructions per second. Millions of instructions per second. So the instruction count divided by the execution time. But since it is million, so I will just divide this by the million. Okay, so instruction count is the instruction count divided by the execution time. Execution time is what? Execution time, as we have covered earlier, and please refer to the previous slides, it is instruction count multiplied by the CPI divided by the clock rate. Instruction count will go with the instruction count, so CPI and clock rate will be on the top here in the denominator. So at the very end, the MIPS will give you clock rates per CPI, and then you divide by 10 to the power of 6. So I might say that this MIPS is 10, that one is 5. Can I say that this one is better than that one? Unfortunately not. Why? Because MIPS by itself does not account for the differences in instruction sets between computers and also the complexity between instructions. So it won't be a fair comparison. I might just say, as a matter of fact, that this can finish this amount of millions of instructions per second. But I don't know, or I didn't compare what is the complexity of each instruction, or I didn't take into consideration if there are different CPUs, what would be the difficulties of their instruction set architecture comparable to each other in this particular case. So it might give me a sense, but it won't be a fair comparison, since CPI varies between programs on a given CPU, and also between CPUs, the instruction set architecture is not exactly the same.